You said elephant, and then you said something else.
What was it? Turtle.
Turtle.
What's the answer? A human being?
No. What do you always? It's a riddle. So what do you always see at a baseball field?
A bat.
I couldn't figure out where the elephant or the turtle came from.
How's it going, Mike?
Pretty good. How's it going with you?
Did you have work today?
I did.
No.
That's why I wasn't at the morning one.
Somebody's got to keep the world going.
I guess.
Well, you might be the only person here.
Really? One-on-one? Everyone else make the first one?
Yeah, except for Anvisa, but she wrote me an email saying she wasn't going to be here.
All right. That's
So
different.
might just be you.
Sounds like a plan. How are you holding up? I'm sure. Were your kids happy about school being canceled, or?
No, I don't think so. I don't know.
I'm sure you aren't that happy.
I expected it.
I mean, yeah, like we're kind of at the epicenter of all this because
yeah,
no one knows what's going on.
Yeah, Solomon, are you happy that school is canceled? Doesn't seem to care.
I don't know.
He doesn't know.
That was my brother. My brother said the same thing.
But yeah, I don't know. It gets old sometimes. You'd like to do something different someday.
Right. Like, what do you do other than sit home and you run out of games to play? Can't really play board games. Can't really go out.
You can do physics problems.
Yeah, true. I was helping my friends with their physics. They were doing thermodynamics. So I was doing that.
Okay.
All right.
Well, we were a couple notes. The link for class will remain stable now.
All right.
I made a recurring meeting, so it'll be the same meeting idea and the same link for the rest of the year.
The rest of the year.
Yeah, I put the review homework assignments in Veracross up through the AP exam, and I don't know what we're going to do after that.
Do we have to do things after it, or?
I think I probably have to pretend somehow.
All right.
But in all honesty, I think we don't really have any pressing need to do things. I don't think.
Right.
So if we look at the review sheet number 1, let's look at your homework.
Electrostatics.
So if we look at your homework here, I think we got through.
We stopped one before, I think.
I think we stopped right around here. I think we did the isolines
Yeah,
question.
yeah.
And I
Yeah.
think we were on C. At least that's what we did in class this morning.
Yeah, I think that's right.
Well, we do know the signs of X and Y.
We know that they're the same. We don't know if they're positive or negative, right?
Well, we do because the well, well, the way you did it, going from 50 to 100, that makes them positive. I'm trying to decide if they could go 50, 40, 30, 20, 0, negative 10.
Yeah.
No, it says the charge on sphere Y is positive in the
All right.
directions. So therefore, X is also positive.
Yeah, because they're repelling, but the attraction is the gravitational force that they exert.
Right. So we do know the signs of X and Y.
All right, I'll change that.
So I would phrase it, the similarity is the difference is, right? Just give the people what they want. Don't, also, there's a good double check for you that you're actually answering the question. As I grade these, and not this one in particular, I haven't graded it yet, but as I grade, a lot of these lately, people just avoiding the actual question being asked is like the most common mistake being made.
I fall in that trap. All right. The difference is this even. All right.
Okay, so I don't know that can you tell me what this question is asking you?
All right. Briefly describe one similarity and one difference between the electric and gravitational forces exerted. All right. So I haven't answered this question yet, which is my problem, but it's asking what's going to be the difference between the forces that sphere Y will exert on the proton versus the forces that sphere X will exert on the proton.
No, the question's asking you what's the difference between electrical forces and gravity forces?
So
Not sphere X and Y.
the forces are going to be similar, but they're going. but the gravitational force is going to be less than the repulsion force,
Okay, so that's a difference, is the size of the force,
the magnitude.
right? Magnitude. So the one difference is, so you just say, one difference is the gravitational force is much smaller than the electrical force.
Michael?
Oh my gosh. Sorry. So the electric force.
And I don't think a lot of this helps you, so you can probably erase most of it.
Yeah, I will.
The electric force is going to be much bigger. Did they say smaller?
I don't know.
In general, electrical forces are much, much stronger than gravity forces.
Because
Or bigger.
gravity.
Did I keep saying smaller? Bigger.
All right. All right, the electric force is going to be much greater than the gravitational force. Oh. Do we have to use an equation to back this up or no?
No. You're going to describe it, and this is because the coefficient of K is much, much bigger than big G. Right. So if you look at the did I put it somewhere? The equation sheet.
I think it's in unit 0.
Ah, there it is.
Yep.
So if you look at the equation sheet, there is the universal gravitational constant, G.
Yep.
That is 6.67 times 10 to the negative 11th.
All right.
It's really, really small.
Yeah.
Okay. And then Coulomb's law constant, K, is 9.0 times 10 to the 9th.
Positive. So,
Okay.
yeah.
So in general, it takes a lot of mass to see any gravity. Like the Earth. The Earth's
Yeah,
pretty big,
Earth and the moon.
right? Those are pretty big objects. So we see gravity when we're interacting with those objects. Every object has gravity associated with it. Like, you know, this paperclip here I'm messing around with
It's
has,
just too
has
small.
gravity, just really is too small. But if I charged it, it really wouldn't take very much of a charge difference to start seeing some effects.
Yep.
Okay, so that's one potential difference between gravity force and electrical force.
This could be like, this is just an off-topic question, but
Mhm.
when they use like the AEDs on people and they shock them,
Yep.
is that why they come up?
I don't think so. I think it's a muscle contraction.
All right. I wasn't sure.
But I'm not an expert on that.
I know you have like so many volts going through your body. All right. Okay.
I think it's an involuntary muscle contraction. I don't think it's an electrostatic attraction, but I could be wrong.
Gravity. All right.
Okay, so that's a difference.
Yep.
So just keep to the point, right? They're asking you for the similarity and the difference. So just spit their own words back at them. The
Rephrase the
difference
question.
is, yeah, the difference is, rephrase the question as a statement. The difference is this. And then you have to say because.
Yeah.
So then the similarity is, right, or a similarity. I guess there are probably several.
Do we only give one?
Yep, that's all you have to give.
All right.
So what's the similarity between electrical force and gravity force?
They're both going to act in opposite ways.
Well, that's a difference.
Oh.
Right, so that's another difference, is that the gravity force is going to be attractive in this case, and the electrical force is going to be repulsive. So that's another thing you could have said for difference, but that's not a similarity.
Decent.
If we go back and look at the equations, you can see the equations for the forces. So right down here, can you see my mouse?
Yep. M1,
Yes.
M2, R2.
So this is the force of gravity equation.
Yeah. That's
Okay.
the expanded equation.
Right. And then this up here is the force of electrical force, the Coulombic force.
They're both dependent on the radius.
The R is the distance between the two
Yeah.
objects, and they're both dependent on it as 1 over R squared.
Yep.
Okay, so that's a similarity. Both forces decay as 1 over R squared.
Can I say directly proportional or decay?
Sure, directly proportional to 1 over R squared.
Yep. All right. What would be another one?
A similarity? Well, the most similarities, so a lot of the similarities that they have are just the same thing for all forces. So it says that you can't say something that generally applies to all forces. But another similarity that they have is that they both act at a distance. All right. So they both act like you don't have to be touching, the two objects don't have to be touching each other in order for the force to apply.
That's where the R comes in, the separate.
Yep.
All right.
Okay. So the change in electric potential energy is Q times the change in voltage. And then the change in voltage is VA minus VB.
Yep.
So that seems pretty straightforward. Okay. Just out of curiosity, why isn't it VB minus VA like you have up here?
Because it's the final destination minus the initial destination.
Okay. And because it's positive, it's going to be repelled by Y and go downhill.
So it's going to be negative.
Right, right. So it's going to go from B to A as opposed to the other way around.
Yep.
Okay. So that's why they throw in the VC there, so that you have to think about which direction it's going. If I come up and look at the little map here,
It's a better drawing.
it could go from B to C, right?
But that would be a negative 20 because you would have to put energy in.
Yeah, that wouldn't be what the proton would do just naturally. You'd have to put energy in for that
Yep.
to happen. And that's not what the question says. All right, released is what it says, not pushed.
Yeah.
All right, so then work is force times distance. That's great.
And then on the equation sheet,
Mhm.
I had a question on one of the notations of the figures.
Okay.
Where is it? It's under the mechanics tab. The change in E equals W. Let me see if I can edit this.
Well, you can annotate my screen. You go up to the view options, and you can
Yep.
say annotate, and then you can make a little mark where you're talking about.
That one.
Yeah, they mean the change in energy.
What's that in the F thing, though? Under the F. I'll draw it.
Oh, so if you are applying a force through this, so if I go like this,
Yes.
right, I'm not doing any work,
All right.
okay, because I'm not moving the object, right? If I take a book and I like push on it really hard, I'm not doing any work if I'm not moving it. So the displacement is a vector.
All right.
Right? So it's going in a certain direction.
Yep.
So your displacement is a vector. And then your force, if you apply a force like this, that's not going the same direction as your displacement,
Yep.
okay, only the part of the force that is parallel to the displacement counts.
All right. I understand it
Okay.
now.
So this double hash mark is the mathematical symbol for parallel.
Or you'd have to do the F D cosine of theta.
Yes.
All right.
But that's dangerous because it depends on which angle you think is theta.
Right.
There's a lot of choices there. You have a 50-50 shot of getting it right.
The elevation or
Yeah.
depression, whatever you
Yeah.
think.
Oh, we have another friend. Anita came late. Hi, Anita.
Hi, Dr. Schmidt. Are you guys discussing the worksheet number 1?
Yeah, just like we
Yep.
did in class today.
Yeah, if we have time, I want to kind of like ask about worksheet number 2, but please go.
Okay.
Thank you.
Yeah. All right. So that I believe. I always click on homework first.
Yeah.
It's fine. It doesn't take me long to figure out where it really is.
I guess I never saw this. Didn't want to ask you if this.
So yeah, so your change in energy is your force times your distance. Your force is your average electrical field, and times Q. So there is your work. Okay, so then.
I didn't get to this part because I just saw it for the first time right now.
Oh, you didn't scroll down.
I didn't. I thought that page break was enough. Distance or just a proton change after. I think student one's right.
Okay, can you explain why? So you just say, so when it says discuss each student's claim, explain why each is correct or incorrect, then just very systematically go through. So you'd say student one is correct. And then you say because blah, blah, blah. And then you're going to have to say student two in a minute. But just focus on one at a time.
Where's Anfisa?
She has a birthday party to go to.
Oh, fun.
During Corona?
Apparently, it's her father's birthday party, so
Oh,
presumably she
yeah.
doesn't have to. Presumably, she doesn't have to leave the house. But I don't. Okay, so Mike, talk to me about this. Okay.
All right.
So
So-
before you spend a lot of time writing, we should discuss.
That sounds like a good idea. All right.
Okay, so the distance between the two is increasing, just therefore increasing the gravitational energy. Okay, fair enough. Is that going to be a big effect or a small effect?
We already said that it would be a small effect, but
Okay.
I was thinking about that. So is it negligible in this case? Because
Yeah, it's very small compared to the electrical potential energy. Now, you all know why I hate the term potential energy. This
Yeah.
is just, exhibit number 2700 of why I hate it. Because it's confusing. The student should say, due to a change in the system's electrical energy as the proton moves through the 20-volt potential difference. Okay, because we're talking about a 20-volt potential difference. So really, we're talking about a big change in electrical energy.
all right. Where's U equals Q? Can I take my equation from earlier
Yeah,
and use it? Because that would be
right. So this is your change in potential energy right here.
Yep.
Right. So you're going to see a change in potential energy. Okay.
yeah.
And student one is saying that this change in potential energy means that the kinetic energy has to increase,
Yes.
right? So is that correct?
Yes.
Okay. Why?
All right, because the proton is being pushed away and not attracted, and not attracted towards the Y particle, so it already has an initial force acting on it, which is the force of repulsion. And then when you add the 20 volts, or when you, yeah,
Okay, so you're saying there's a force acting on the proton,
correct.
and that force is moving the proton some distance.
Yep.
Okay, so that's a force applied through a distance.
Yeah.
That's called work.
Yes. And then your work.
Okay, so you're saying that the kinetic energy is increasing because positive work is done on the proton.
Yes. Because the proton's not coming closer, it's getting farther away. So
Yeah.
number 2 is right.
So you're saying student 2 is correct because of what you just said.
Yeah.
Right.
Student
So
1's
you can
wrong.
start with student 2 then. We'll come back to student 1. Why don't you erase what you have here and write out an explanation of why student 2 is correct.
All right. I think
Okay,
that's
so it's from the way that you're phrasing things, I'm not sure you entirely understand what work is.
work is a force applied over a distance.
It is, okay. But work is the transfer of energy,
Yes.
okay. So when the work is, so work I wouldn't really say that the work adds force. So the way you're phrasing things, it's confusing about whether or not you mean that the work force is different than the force of repulsion.
I'm trying to say that they're acting together.
But they're the same thing. Okay. The force of repulsion is what's doing the work.
All right.
Okay, that is the force. When I say work is equal to force times distance,
So the force of repulsion
in
times
this
distance.
in this case, it's the force of repulsion.
All right.
There isn't any other force coming along and doing this work. So you're saying it adds force in the same direction as the repulsive force. That's really implying that there's two different forces. It's
Yeah,
really
I was
confusing.
kind of thinking that.
Right. And since work is the transfer of energy, whenever you have work done, that has to be a transfer of energy into the system. Okay, I think I may have stopped syncing on my part.
No, my surface is not working the best. So it's probably my end.
But that looks good. So the work is added to the proton. It increases the energy of the system. Since we know the potential energy decreases, it must be the kinetic energy that's increasing, or something
Yep.
like that. All right, so now let's talk about student one. All right, so is student one correct or incorrect?
He's partially correct, I'd say,
Okay. So why partially correct?
because the potential energy is going to change, but with this problem, it's negligible to student, or it's not really the main form of energy. Maybe a percentage, a very small percentage, will be transferred to potential, but the majority is going to be kinetic energy.
Okay. So when I taught, the freshman physics energy, I encouraged them to make a bar graph of the energy at different points in space. All right. So if we have a bar graph of the energy present in the system at the beginning, okay, there's going to be electrical potential energy, and then there's going to be gravitational potential energy, and then another possibility is to consider kinetic energy. Okay? But there's going to be no kinetic energy at the beginning. And the gravitational energy is going to be really, really tiny.
Yep.
Okay? But there's quite a bit of electrical potential energy at the beginning. Okay, that's the chapter. That's what happens whenever you have charged objects near each other. So you have a lot of electrical potential energy. Okay, and then time happens. Okay, there's a 20-volt difference. What happened to the electrical energy?
It's going to decrease
It's going to decrease. So now maybe I only have 3 boxes worth.
because it's farther away.
Okay. And so if you count them up, I got 6 boxes here.
Right.
And I only have 3 boxes now.
Energy can't be created or destroyed.
Ah, right. That's the first law of thermodynamics. Energy can't be created or destroyed. So where did that energy go?
To gravitational.
Well, it didn't. Gravitational, we said, was infinitesimal in this case.
So it has to go to kinetic.
So it went to kinetic. Okay. So that energy is going to kinetic. Okay. Now let's read what student 1 says. Student 1 says that if the system is defined as the proton and the spheres, the increase in the proton's kinetic energy is due to a change in the system's potential energy.
Potential energy is not changing.
Well, they mean electrical potential energy. So is that why the kinetic energy is growing? Because the electrical potential is going down?
Yes.
Yeah. So student 1 is correct.
So both are correct.
So both are correct. They're just different ways of looking at the same idea. Okay, excellent. So now we look at number two, worksheet number 2 here quickly. I think Anita has a question on that.
All right.
Yeah. Oh, these are mine.
Mhm.
Yeah. I was just wondering for this one I'm okay, but if you guys want to talk about it, yeah, that would be great as well. But for this one, I was not sure about what to set as the slope.
Well, so here, Mike, we have 2 disks, disk 1 and disk 2.
All right.
Okay. Um, disk disk 1 has a known charge on it, Q1.
Yep.
Okay. Disk 2 is rubbed with a cloth to become charged, and then they're going to put some amount of charge onto disk 2, hopefully, and then they bring disk 2 close to disk 1 until it begins to slide. So the reason it's not sliding at first is because there's friction.
Yep.
And eventually the electrical force is going to be a little tiny bit bigger than the friction force. And then it's going to start sliding.
All right.
So then the question is to make an equation relating the distance d that the thing starts to slide to Q2. That the charge imparted by like one rub, I guess a genie's worth of rubbing or something. I don't know how they quantify a rub. Okay. So where would you start your analysis here, Anita?
Yeah, I did. I kind of don't get what it is saying. Like, why would there be sliding? Like, why would it slide? Is it because of the force?
Yeah,
And, like,
the electrical force. So draw a force diagram.
okay, yeah. I'm just writing this down. So we want to find the charge. That means we have to measure the distance.
The distance is something that you can measure, yes.
So, like, how would measuring distance help?
Well, it's just maybe if you wrote an equation that might be more clear. But you have to make a force diagram in order to even think about the equation that might be relevant.
Yeah. So, but like, is gravitational force like ignored here?
It's going to cancel out with the normal force all the time.
That's true. So we don't really need to draw that, but we have to draw. But we don't. We also don't know like which way it is sliding, right?
Nope, but it doesn't matter because the static friction force is always going to point the other way, right?
Is there friction force?
Yeah, it
Okay.
even says so. Let F be the magnitude of the maximum force of static friction on the disk.
Yeah. So, so like, if it's this way. And then the force would point the other way, and that means can you see what? Can you see that I'm writing?
Yep.
Okay. Yeah. So we want to find the, because if they have the same charge each time, that means the distance would be the same for all the cases.
No, they don't have the same charge each time. There's a different number of rubs.
Yeah, I mean like,
Q2 is the net charge deposited on disk 2 as a result of rubbing the disk once.
yeah. So
That's not terribly important. What I want to know right now is what the force diagram looks like
between the two.
for disk 2 just before it starts to slide, or disk 1 just before it starts to slide.
Like just this. Just this.
What kind of force is that?
The electric.
Okay, so the electric force is pushing disk 1 to the left.
Yeah.
Okay. So why doesn't it just fly away? It's not sliding right now. I said just before it begins to slide.
Because there's a friction force that cancels.
Okay. So where's the friction force?
It's not showing up there, but I just wrote it.
Oh, okay.
Yeah.
Yeah, it can take a little while to sync.
Yeah,
Sometimes.
but yeah, I just draw it the other way, and at that instant, they should cancel out because the disk is not going anywhere, right?
Okay. So then you keep moving disk 1. You move disk 2 a little bit closer. What happens?
The disk starts to slide left because it receives a stronger electric force.
Okay, so at that point, you know that the electrical force is infinitesimally bigger than the friction force.
Yeah.
So basically, it's equal to the friction force.
Yeah.
So you can write that down as a statement. Force of friction equals electrical force.
Oh, it's not showing up. That's so annoying. Do you want me to share my screen?
Yeah, if you can, if you're not using
I can totally do that.
a lot of people seem to be using different devices for Zoom than they do their work
Yeah,
on.
that's me. But I have to find. Wait, am I not opening my window? Page is it? Yeah, here. Here. Yeah, there we go.
Okay, so the force of friction equals the electrical force. And then you can write those as the force of friction is just the force of friction, but you can write the electrical force as a component equation with things in it that you know, like Q1 and Q2 and D.
So, like here. But isn't Q1 and Q2 equal in charge or not really?
No.
Okay, never mind. Okay, Q1, Q2 over D squared.
And and so Q2 is really the charge on the disk,
Yeah.
right? And Q2 is defined in the problem as being the amount of charge from one rub. So how much charge is on the disk?
1 Q2.
Well, why is it just one? Like you do this several times, right?
Oh, so like each time it is rubbed, there is more charge.
Yep.
Well, it does not ground before it gets another. Oh, then I might have interpreted the question wrong because I thought it was like first you rub it with the
Well,
cloth.
so they say they discharge disk 2 and repeat the process, each time counting the number of times they rub sphere 2. So the charge on sphere 2 is going to be Q2 times the number of rubs.
So it's not always Q2. Oh, that makes a lot of sense. Number. Oh my god, I'm not raising. So like we can write charge on disk 2, charge on disk 2 after like n times would be nq2.
Yep.
This is so messy. Yeah.
Okay, so now you want to relate D. So in your expression, where should that n be? So you have the force of friction.
Yeah.
Right? You have the force of friction is equal to this thing. So where is your n going in the equation?
On the top?
Yep.
Yeah, it's not showing up again, but yeah, here we go.
Okay. So now the question is to make an expression relating D and Q2.
Mm. Like this.
You lost the force of friction.
Okay, yeah, that's true. I did forget about that. Like this. Not showing up again.
Yep, like that.
Yeah.
Okay, so there's your answer.
Yeah.
Okay. Let's go back to the experiment because I think we did the experiment in class, and I just want to make sure Mike has a good idea about how to do the experiment. Okay, so Mike, let's look at this question. So we have a conducting disc up here, an insulating rod, a stand, and the conducting disc has been given a charge. And you have some equipment, several plastic spheres that are attached to a string, a cloth that can be used to give the spheres a positive charge, a different cloth that can be used to give the spheres a negative charge, and a grounding wire. So can you just describe to me a procedure that the students could use to determine the sign of the charge on the disk?
They know the charge that the rod can give, right?
The rod? The rod is insulating.
Oh,
It's not
yeah.
charged.
Oh yeah, so they could just take the positive sphere on an insulating string and bring it closer to the conducting disk and see what happens, whether it attracts or repels. And by doing that, you can figure out what the charge of the conducting disk is, unless it's a neutral.
Okay. What if it is neutral?
If it is neutral, you could try grounding it. And
Well, so I mean, so first of all, make sure you say that you have to charge the plastic sphere by rubbing it with the cloth.
cloth, yeah,
Okay. So you make the sphere positive, and then
yes.
you bring it near the conducting disk. What would it tell you if there was attraction between the conducting disk and the positive sphere?
Then the conducting disk would be negative or neutral.
Okay. And so is that enough of an experiment to tell you the charge on the disk?
No.
So what else do you have to do?
You could use the negative, or
Yep.
yeah, you could use the negative disk, and then you could ground it and see if there was any form of attraction between the two.
What would you want to ground?
The sphere.
Okay. Just to make sure it's neutral before you make it negatively charged?
Correct.
Okay. So then it becomes negatively charged, and then what might you see with the negatively charged sphere?
If it's neutral, you'll see repulsion.
Attraction. So if the negatively charged sphere,
Yeah. You're right, because all the if this is like, I got you. Kind of like that.
yeah,
All the electrons are going to move to the left side.
yeah. And so you induce a dipole moment, is what it's called, and that makes an attraction.
Yep.
Okay. So attraction alone is not enough to tell you if it's charged.
Yep.
How can you tell if something is charged?
If it exerts a force on another object,
Not an attractive force,
a repulse.
repulsive force.
Yeah.
So if you bring the positively charged sphere nearby and it repulses from the disk, that tells you what about the charge on the disk?
It's charged, and it would be a positively charged disk.
Yeah. And if the positively charged sphere is attracted to the disk, does that tell you that the disk is negative? For sure?
No.
No. You have to bring the negatively charged sphere nearby and see if it
Yep.
is repulsed. And
Right.
then that'll tell you. So the grounding wire isn't really necessary here because you have several identical plastic spheres, so you can just use different ones.
All right.
Okay?
Yep.
All right. Thanks so much for coming, Mike. Appreciate it.
Thank you for being here.
Well, maybe see you folks tomorrow morning. No, wait, Friday morning.
Yeah. Dr. Schmidt, can I ask a quick question about the second?
Yep. Okay.
Yeah. So if we plot, because the distance would be the square root of something, if that makes sense. Like the distance is the square root of KQ1 times NQ2 divided by square root of FF, friction force.
Can we delete new section 2 here?
I have no idea who got this, but yes, please delete it. Thank you.
Okay. Because every single time I don't know where you're Put in your homework. Okay. So you can't plot. So on the horizontal axis, you can plot. So you're creating a graph. You want to determine whether the same amount of charge is deposited on disk 2 each time it's rubbed. Okay. So if this equation up here is to be a straight line equation, what form should it have?
If it is to be a straight line, that means we have to plot like the direct relationship.
Right, so there's a mathematical form that it has. It's like y equals
Let's be.
mx plus b. Okay. And what would b be in this case?
B would be 0.
B would be 0. So get rid of that, right? And y would be d.
Yeah. And then,
So what's going on the vertical axis then? Y is the vertical axis.
yeah. Y is the vertical axis, and that means x is going to be nq2, the square root of nq2.
Well, depends on what you're plotting.
Yeah.
Right. So looking at this stuff here, so y is so d is going on the vertical axis,
Yeah.
and what's going to be going on the horizontal axis? What one thing? You got a bunch of stuff here.
Like just nq2, the square root of nq2.
Well, that's not something you can measure.
I mean like the slope.
So that's not something you can put into a data table and not something you can plot.
Yeah, this is the slope, right?
Sure, that would be the slope if you could plot in Q2, but you can't. You don't have any way of measuring it, no way of counting it.
Frictional force?
No way of measuring that either.
Then that would be KQ1.
No way of doing that either.
Yeah.
So think about the experiment. What are you measuring? What can you plot? You're measuring D. So D is a perfectly valid thing to plot on your graph because you are measuring it.
Yeah, so D would be on the x-axis.
No, D's on the vertical axis. D is Y.
But like, are you talking about like what can we plot on the x-axis as
Yeah.
the change variable?
What can you plot on the x-axis as a variable, something that you measured?
Do we measure Q1?
Nope, don't measure Q1. Even if we did, I think Q1's given, but it would be the same every time. So your graph would look like, this is what your graph would look like. You plot it, and every single time you get the same value, so it would look like this.
That makes sense.
And you would always get Q1 being the same number over and over again. So you get a vertical line. Is that like y equals mx plus b?
So we should plot NQ2 over FF together.
No, we can't plot that. We cannot measure that.
Yeah.
What are we measuring? You have to plot something that you measured on the horizontal.
N.
N.
That's like the only thing you measured.
That's what you measured, right? But would that give you a straight line according to this graph?
Yeah.
No.
But the square root of N.
The square root of N.
Yeah.
So if you plot the square root of N, then your equation is like this. D is equal to the square root of K Q1 times Q2 over the force of friction
times square root of n.
times the square root of n. And now your x is
The square root of n.
the square root of n, and your slope is this mess.
Yeah, and
Okay? So now you have to think about how your graph could be used to determine whether the same amount of charge is deposited on disk 2 each time it's rubbed. What is that?
Q2.
That's Q2. So effectively it's asking you, is Q2 a constant value?
So it's asking if the slope is constant because everything else must be constant.
Yeah, K is constant, Q1 is constant, and the force of friction is constant. So therefore, if Q2 is constant, this will be a straight line. If
Yeah,
Q2 is not constant, then it will not be a straight line.
yeah. So we're just going to, I'm just going to write about that.
Yep, that's your job.
Yeah, that's my job. So, gotcha. Do you think this one is a hard problem?
Eh,
Or is it something?
we did something I remember doing something very similar in class not too long ago.
Okay.
I think it was maybe a few months ago.
Oh, I might have to thought about that. I remember the first experiment though, like when we did about the conducting disk.
And we had to determine that something was constant or not. And if it was, I don't remember what it was, but it was a very similar thing
Yeah, I feel like,
where you had to say that this was the slope. And if the slope was constant, then the thing we were trying to determine was constant. I'm pretty sure it was how many number of times rubbed.
oh really?
Yep.
Okay.
They're charge deposited by a rubbed object. So they like to ask about it.
Yeah, so it's good if we figure this out.
Yep.
Thank you, Dr. Schmidt.
Thank you.
Bye. Good
Take
night.
care. Good night.
See you on Friday.